This is John Van Omen coming from sunny Nevada. I've made a bunch of posts in the last few days in regards to the Square Pegs thread on DIY audio, and also in regards to a thread I wrote a long time ago about making your own compression drivers. And I reread them today, and after rereading them, I realized that I'd made a lot of assumptions about how deeply the folks reading the threads had studied it. So I thought it might be a good time to kind of do an overview of what I'm trying to do here. And normally I just type this up and put it on the forum, but I've been super busy lately. Literally just finished something for work, hence the outfit. And because of that, I thought it might just be faster to sort of discuss where I'm going with it. Okay, so the first thing, kind of the overarching thing, is that I think Mabat, I don't know if I'm pronouncing that right, Mabat, I think that his software is like one of the greatest things that anybody's ever contributed to the community. It's really changed the game, in my opinion, because, I mean, not just that you can make waveguides, but the fact that you can simulate waveguides with it by leveraging ABEC. And up until then, before his software came out, even if you knew how to use ABEC, it was quite a bit of work to take advantage of the software. There's a big thread over on a German forum which gets into how to use ABEC, and that thread it's great, but it's not really approachable. Okay, so the German thread is great, but ABEC isn't particularly approachable. I think what is especially awesome about ATH is that it gives everybody the ability to leverage ABEC to do simulations which were beyond the reach of, I'd say, at least 99% of the DIYers out there, and it makes it pretty straightforward to get good results. All right, so then that begs the question, well, why aren't you just using ATH? And I do use ATH all the time, but kind of my thing, just with everything. Whether it's audio or my day job or car stereo. The fun part for me is reverse engineering things. You may have noticed that I'm often the first person to take some Danley design and try to figure out how it works. That's what's fun for me. So what I'm about to get into, this isn't necessarily if you're just going for, I want to have the smoothest sounding conventional speaker I possibly can. Honestly, you should probably just stick with the stick with the ATH thread. It's going to serve you well. But if you're like me and you like to tinker, let's go. Cycloid. And apologies for the dogs and the air conditioners. Sunny Nevada is indeed warm right now. I think we're about 100. Okay, so the first thing is that you've seen a lot of work that I've done to try to reverse engineer the Paralines. This has been going back to probably about 14 years now. And that was one of my first thoughts when I started working on it again in the past few weeks, is that I'm making assumptions that people have followed this thread for 14 years, and I'm sure a few have. But what you're seeing in the recent updates in the Paraline thread, which is called Square Pegs, in that thread, I've basically found a way to generate the shape of the Paraline using a Python script that I generated with ChatGPT, that I generated with an LLM. So that was really useful for basically getting the shape right. And though I kind of, how to put this, I've been a little bit dismissive of the Paralines in that thread because I hadn't achieved great results myself. But I think that Todd did a great job of summarizing why I wasn't getting great results, and he was right. So if I really should go back and edit everything I said in the whole thread, but got a lot of stuff on my plate. So that's the first thing. Everything in the Square Pegs thread, you want to kind of consider it in the scope of the fact that there were some fundamental errors made early on. This is also where the LLMs come into place because my advanced math is just non-existent. I couldn't do what I did with the Paraline, with the Square Pegs thread, if it wasn't for ChatGPT. It basically allowed me to leave the advanced math to ChatGPT, and I could kind of focus on describing what it is that I wanted. This is kind of the magic of LLMs, is that you can use natural language to describe what you want the LLM to generate for you, and you don't necessarily have to fixate on how do I get it to generate this. It's more about describing what it is that you're after. Okay, so hold that thought. So I did I think a pretty good job with that in the past few weeks, and then I wanted to take it to the third dimension and do something which was more similar to the ATH software, though admittedly much cruder. My goal with that Python code was to then modify it so that you could basically pop in the parameters of what you want it to build, or generate is more accurate. Pop in the parameters of what you want it to generate, and then it would do that for you. Again, very similar to ATH, but instead of having a conventional compression driver at the throat, you would have a Paraline at the throat. Okay, so if you've been following the latest updates to the two threads, I stumbled across something thanks to, again, Mabat, and it kind of blew my mind because it allows for something that I didn't realize was possible. So let me describe that. All right, so the Paraline, what it fundamentally does is it takes a spherical source and it turns it into a wavefront which can be ribbon-shaped, but more importantly, you can also generate a wavefront which is like a curved ribbon. And note that curved ribbons pretty much don't exist. So when you look at like a line array at a concert or something like that, you'll notice that the line array is composed of a number of elements. And the reason why they use a number of elements is for a couple of reasons. The first one is that the height of the array is going to determine how low it controls directivity. So, for instance, let's see, 1,000 hertz is 13.5 inches, 100 hertz is 135 inches. So if you wanted to control directivity down to 135 hertz, your array would need to be 10 feet tall. So that's pretty tall. And that's why you see these giant arrays in concerts. But then another thing why you want the very tall array is that the addition of the elements increases the overall output. Depending on the wavelength, it improves the efficiency. But bottom line, oh, and I forgot, when you curve the array, you can change the shape of the wavefront. And this is pretty important, especially for a home. So if you followed the CBT threads, oh my gosh, I'm cramming so much stuff in here. I feel like this is a homework assignment. But if you follow the CBT threads, you'll see that the CBT arrays look quite a bit different than a conventional straight line array. And so the reason why the CBT array is curved is that improves the response as you move across the angle of the array. It basically makes the whole array behave closer to a slice of a point source. And let me describe what I mean by a slice of a point source. So a point source speaker radiates sound spherically. And so if you look at obvious one would be something like a Danley Synergy horn. It is basically producing a portion of a spherical wavefront, but a traditional Danley Synergy horn is producing, again, spherical, but it's a part of the sphere. So if you can visualize a sphere, this is where I should spend an hour like making some illustrations or something, but if you can visualize a sphere, the Danley speakers, then you take a cone, and the cone goes into the sphere, and that cone of sound is what the Danley speaker generates, a conventional Danley speaker. This is pretty cool, but there's one downside, and that is that the sound falls off much more quickly when it's radiating spherically. Okay, and this is just, again, I'm not a physicist, so I don't know what it's called, but basically, if you have sound that's radiating in every direction, it's going to fall off faster. I guess that's inverse square law, right? That is what the Synergy horns do, the conventional Synergy horns. With a line array, again, you're getting like a vertical ribbon of sound, and if it's flat, it's just going to project in one direction. So it's not going to go up, it's not going to go down, it's just going to go straight forward. And then the key thing here is that because it's only controlling directivity on one axis, the vertical axis, the sound can then radiate to the left and to the right, because there's nothing stopping the sound from radiating to the left and to the right. But vertically, it's producing a wavefront, again, like a ribbon. So if you could visualize like a ribbon that goes from like the bottom of the array to the top of the array, and it just radiates through the room, that's what a flat array does. And then when you curve the flat array, it changes the beam width of the array on the vertical axis. Whew, that was a mouthful. Anyways, if you got questions about that, just post them on after I post this video, really. I'd prefer if the comment, well, I was going to say I prefer if the comments aren't on YouTube, but actually I don't care where you put them. All right, so let's get to what's so magical about what was posted last night on the Square Pegs and the DIY compression driver thread. Okay, so here's the kind of magical thing that I found last night. I'm sure a lot of people are reading and thinking like, well, we figured this out 30 years ago, but it was cool to me. Is that, let's see how to put this. If you're trying to make a vertical array, a problem that you will run into, well, actually, let me adjust that. If you're trying to make a speaker that has wide horizontal beam width and narrow vertical beam width, the problem that you're going to run into with something conventional, like a Synergy horn in particular, is that the horn needs to get very big. I think one of the best examples of this is the Klipsch Jubilee. So the Klipsch Jubilee has an asymmetric pattern that is wider than it is tall. But if you look at the Klipsch Jubilee, its it's freaking huge. I can't really imagine any scenario where my wife would let me stick that in the living room, and I don't even know if I want it in my living room. But the Klipsch Jubilee is a great example of a very well done conventional waveguide with a single compression driver at the throat. Okay? So what we do in arrays is that instead we use a number of small waveguides and we stack them vertically. So by stacking them vertically, we have to invest in a lot more compression drivers, which of course carries an expense and it's heavier. That's not even really a big deal to me. I think one of the things that I particularly don't like about that solution is I hate speakers where if there's like one part that fails, you might not know that it failed. And so then you have a speaker that's just not performing to 100% the entire time that you have that. And this is a big problem with arrays because you could lose a single tweeter and it might just sound a little bit off, but you might not be able to detect it with your ears. So now you got a speaker that's like a homework project. You got to, bust out the mic and every once in a while make sure that everything is running properly. This aspect of line arrays is also why I'm not a big fan of tube amps. It's not that I don't really like the sound. It's just that I don't want to have an amplifier that I have to tune up. I got too much stuff going on. I'm just not interested. I just want it to work. And the other problem with line arrays is that it's pretty much impossible to get the high frequency drivers close enough together. The reason why is that drivers begin to beam when the length of the sound that's being radiated by the driver is smaller than the driver itself. So for a 1-inch tweeter, 13,500 kilohertz is 1 inch long. And so because of this, when you have a vertical, or actually any line array, whether it's vertical or horizontal, basically when you have a two-dimensional line array, it's all but impossible to get really good high-frequency response above the point where the diaphragm of the driver itself is too large. And so if you looked at the original CBT speakers, they actually used a full-range driver, which was intended for, I think, phones and laptops and things like that. But they used that because it was so small. So if you look at the original Keel CBTs, you'll see that the line of tweeters is extremely small. Okay, so what is typically done in commercial line arrays and also in some home line arrays, well, actually, oh no, Tom's gonna be mad at me. I almost called a Danley speaker a line array, and no, Tom's never gone mad at me. He's the sweetest guy ever. But what is done in those commercial line arrays is that they use some kind of a device to change the wavefront. And there are a zillion of these out there. There's the VDOSC from L Acoustics and the Paraline from Yorkville and Danley. Those are the two that I've been particularly focused on. Of course, there's also ones from 18 Sound. There's ones from JBL. You name it, somebody's got one. Now, the problem that all of those face, and I don't know how you pronounce his name, Folgott. He did what I think is some of the best documentation of the superiority of planars and ribbons to these types of waveformer devices. Is that when you're using some kind of a waveformer, you can't get the sound coming off of the diaphragm of the tweeter or the compression driver. You can't get that sound to go through the device without some type of diffraction, and Another issue is that it's almost impossible to get the path lengths perfect. So the Paraline does a really good job of getting the path lengths right, but it's going to run into the diffraction problem because there's a 180-degree bend in it. The L-Acoustics VDOSC is going to have a different problem, which is that the sound has to make a 90-degree bend. But as you can see, these are just varying degrees of the same problem. One does a shift of 180, one does a shift of 90. Okay, so due to this particular issue, if somebody can figure out how to take a conventional tweeter or a conventional compression driver and get it to produce a flat wavefront, that's going to be, a really big deal, especially if you can do it without bending the waves. And if you've got to bend the waves, bend them as little as possible, because it's the bending of the waves that causes diffraction, or at least that's the theory proposed by Earl Geddes. I'm not sure if I'm pronouncing your name right, Earl. I apologize in advance. And I tend to agree with Earl. I had the Gedley Sumas when I first started messing with my Paralines, and something that I noticed was that I would be listening to the Sumas for like sometimes 3 or 4 hours a day, and I never felt like I was fatigued. But I'd listen to my Paraline designs, which again were extremely crude. Todd is right. My designs were crude. They were not great. But I found that I wanted to run and turn them off after like 10 minutes, even if they measured well. And then that begs the question, well, if they measure well, why do they sound bad? I'm not saying that they sound bad. Correction. If they measure well, why do they not sound as smooth as a conventional dome tweeter? And the answer to that, I believe, is the diffraction, and you can see the diffraction in the cumulative spectral decay of a waveformer. And again, he's got the receipts. Go read his articles. All right. So, did anybody think it would take a half hour to get to the point? I guess that's just my style. So, what I discovered with what Mabat posted last night is that you can change the wavefront inside of the phase plug. And you're probably thinking, ooh, why is that a big deal? Okay, so first let's cover what a phase plug is. So a phase plug, especially in a compression driver, is used so that you can take the diaphragm of the compression driver and you can fit it through an aperture which is smaller than the diameter of the tweeter in the compression driver. So, keep in mind, a compression driver is just basically a tweeter that is compressing the sound coming off of the diaphragm, hence compression driver. You can also make compression mid-ranges. You can do all kinds of funny things. I generally prefer newer compression driver designs where the phase plug, I guess you'd call it open. I've posted pictures before of like a TAD compression driver from like 25 or 30 years ago that had been sawed in half. I actually found that out here at the Consumer Electronics Show. I was at the TAD booth, and they just happened to have it there, and I took a picture, and I've used that picture like 1,000 times now. It's an incredible reference. But I'm not a big fan of those compression drivers with high compression. And what I mean by high compression is literally that the sound is being more compressed. Whereas with the newer ones, most newer compression drivers have much less compression. So if you look at like a modern BMS ring radiator or something like that, compression's much lower. I could maybe speculate on why lower compression sounds better, but it kind of gets out of my comfort zone. Somebody else has probably written an article on it. So we can take the diaphragm and we can reduce it down to a smaller size. So for instance, if you had a diaphragm that was 2.5 inches in diameter and a compression driver, you can cram all of that sound through a 1-inch hole in the compression driver, which is called the throat. All right. There's two types of throats. Actually, there's 3 types of throats in a compression driver. The first one is that the wavefront expands, and this is 99% of all compression drivers. The sound is expanding as it exits the compression driver. The second type would be just straight, and there's a few. BMS has some compression drivers that have no expansion. Basically, the exit is 0 degrees, and then if you want to make the wavefront wider, you would attach a waveguide to that compression driver to then take the wavefront, which is flat, and have it expand. And then the last one, which I've only seen once, or I thought I had, is a phase plug, which is actually reducing the coverage angle. So basically, it's taking when the sound wavefront exits the compression driver, it's not expanding and it's not straight, it's shrinking. Now, one would expect that this would focus the sound at a specific point, but Mabat, again, clued me in that though it looks like it's shrinking, it actually isn't. What's actually going on, and I posted the link in the, I believe in the DIY compression driver thread, and Mabat also posted it in his thread, the ATH thread, is that the phase plug in this specific compression driver, which is from Celestion, that phase plug, it looks like it's shrinking the wavefront, but it's actually altering the path length. You really got to look at the pictures to see what's going on, but because of what it's doing, it allows us to do some really interesting things with compression drivers. But I think what's even more interesting is it allows us to do some really interesting things by making our own compression drivers. And I've got an entire thread on DIY compression drivers, and I've never seen anyone else do it, but there's some good stuff in there, and it worked. You can look at the measurements. You can take a conventional tweeter, and you can do what appears pretty much like a compression driver, but you can control all the parameters. So you can. And what I mean by control the parameters is that you can change the F3. You can make it play lower. You can make it play more efficiently. You can make changes to the response so that it can handle more power, and more power not thermally, but because of the excursion. You can do some absolutely crazy things if you start making your own compression drivers, and I'd say really like making your own compression drivers to me seems a lot more logical than even making your own subwoofer boxes or making your own mid-range boxes. Because with mid-ranges and subwoofers, we can change the response electronically, and it's pretty effective. But with compression drivers, there's only so far you can get until what happens is, if the wavefronts aren't right, there's not really anything you can do. And that's arguably kind of unique to tweeters, that once you get pretty high in frequency, it becomes very, very, very difficult to combine them, because the wavelengths are so short. So all of these line arrays, and they're all a compromise. The only way they could truly not be a compromise is if somebody could come up with a tweeter that could handle a lot of power and get very loud and was about maybe 1/4 of an inch in diameter. And we all know that's not going to happen. So I've already established years ago that you can make your own DIY compression drivers by taking a conventional tweeter and putting a conventional phase plug on it. The phase plugs from that article are largely just copied from other phase plug designs. So, for instance, one of the designs that I copied was from, I believe, a BNC compression driver. So, in the thread, I understand about path lengths and things like that, but I didn't have the ability to do boundary element modeling, and it's boundary element modeling that really takes us to the next level and allows us to do things which were basically impossible 20 years ago. I'm not going to get into boundary element modeling because I thought this was going to be a 15-minute video, and I think I'm probably approaching 45 minutes now. But the bottom line is that the original thread about DIY compression drivers, that worked. It could work. You could do it right now. Take any of the designs out of there, have at it. Build your own. In order to do it, you're going to need to be you have to learn some kind of 3D software, but it's not as hard as it looks. I like 123D because it's free and I'm cheap. I know there are alternatives out there, and I use weird software, but I like cheap, or I like free, or I like open source, and I don't like Blender. I tried to learn Blender. It's just bleh. So I recommend 123D because it works for me, but something else might work for you. All right, but so the magic of making a conventional phase plug is that you can take you can basically replicate to a great extent what we could do with a conventional compression driver, but you can change things. Again, you can use you could have a design that's low efficiency and wide bandwidth. You could have a design that is oriented to play very high. You can do all kinds of weird things, and keep in mind that the compression driver market itself is largely oriented towards pro sound reproduction. So we are buying compression drivers which are completely maximizing output when we don't always want to maximize output. Sometimes we want to do something else. And the something else that I would really like to do, based on the information coming from last night's posts, is that I would like to create a compression driver with a wavefront at the exit that is not symmetrical. And the reason why this is so special is that if we can create a wavefront that isn't symmetrical, then we can mate it to a waveguide that isn't symmetrical. And you're probably thinking, what are you talking about? Like, we've had 60 by 40 waveguides since like the beginning of time. Well, go model them with ATH. Go ahead. Model a 60 by 40 waveguide with ATH and tell me what you see. Because what I see is that those 60 by 40 waveguides rarely behave as you expect. You will find that it's really hard to get an asymmetrical waveguide to be well behaved across the entire bandwidth. And you think, well, why is that? Well, a big part of the reason that it's hard to get a 60 by 40 waveguide to be well behaved across this entire bandwidth is that the what is driving it at the throat should also be asymmetrical, and basically you need to get everything right all the way up to 20 kilohertz. And keep in mind that it's something like 0.6 inches. 20 kilohertz is really small. So this is something where this isn't something you're going to design by hand. Like, this has to be done using 3D software, 2D software, boundary element modeling. This is like next level stuff. I wouldn't be surprised if a lot of loudspeaker manufacturers aren't designing at this level. If you look at the threads, particularly with people who are using ABEC to model some complex devices like Paralines, maybe I'm missing something, but it seems to be about 5 to 10 people in the entire world. This knowledge isn't super common, and that's where I come in. I'm not selling anything. I don't do consulting. I just like reverse engineering stuff. I mean, I could have bought a KEF speaker a long time ago. I could have bought a KEF blade or something like that and just stuck it in my living room. But I like making stuff. I like designing stuff. I like tearing stuff apart. And that's what I intend to do here. Now, getting back to the specifics of the phase plug, I haven't designed it yet, but my feeling is that it's gonna wind up having a elliptical throat on what will be a DIY compression driver. I don't think this has ever been done. And if somebody out there will chime in and tell me that why this is a really bad idea, I'm all ears, because it seems kind of obvious to me that at some point somebody would have made a compression driver with an elliptical throat, because if you're going to have a waveguide which is asymmetrical, it really seems to me that the wavefront that is entering the waveguide should also be asymmetrical. And then that begs the question, why should they both be asymmetrical? Okay, so the reason that the output of the compression driver and the input of the waveguide should both be asymmetrical in a waveguide which is asymmetrical is because of path lengths. Okay, so imagine a speaker and you have like a series of rays emanating out of the waveguide. You know, you've got one going down the middle, you got one going down the side, you got one going down the other side, you get a ray going towards the floor, you got rays going everywhere, right? Okay, so if your throat is symmetrical, but your mouth is asymmetrical of your waveguide, you're going to have little path length differences. The ATH software can help you a lot in this respect. I mean, like it gets you, you know, again, ATH is really good. Like, I'm not telling you to not use it. I'm telling you that I like reverse engineering stuff and I like problems like this. So if your goal is just audio nirvana, go build something with ATH or buy one of his designs. But from my understanding of how waves travel, we want that asymmetry, because if we don't have that asymmetry with an asymmetric waveguide, what we will run into is these little path length differences. And it's those little path length differences that add up, and those little path length differences that cause, especially in the very high frequencies, causes a ragged response. You can go over to Audio Science Review and you can look at the measurements from the Klippel of the JBL CBT speakers and look at the high frequencies. They're a mess. They're not good. But there's still a magic to the CBTs. Like, I've heard the CBTs. They do something special. But the treble just isn't there. The treble sounds like a little bit rolled off, even when it measures flat. There's just something wrong with the upper treble, and then you can see it in the measurements. The measurements of the upper treble look terrible. So what a asymmetrical throat on a waveguide combined with a asymmetrical exit on a compression driver is that then we can keep those path lengths ideally just about perfect all the way down to the surface of the tweeter diaphragm itself. And then this brings up one last thing. Okay, so another solution that can work very well here is to just shrink the size of the compression driver. And particularly if you look at the Tritonia ATH waveguide, which is out there, you'll notice it performs really well. And that is, a lot of that is because, how to put this? So a lot of, especially modern compression drivers with a throat of an inch, if you take them apart, I mean, literally get out your screwdriver and pull the thing to pieces, you will often find that there's a fairly wide angle inside of the compression driver. And what I mean by that is that you've got the tweeter diaphragm inside of the compression driver, and then you've got the exit of the phase plug inside the compression driver, and then there's a little stub that causes the wavefront to expand. So when you look at a 1-inch compression driver, I use the ND151M from Eminence as a great example of this. If you take that thing apart, it behaves more like a compression driver, which has got a throat of 0.75 inches, because there's this stub that's built right into the compression driver. And so when you're looking at some of the great results of the Tritonia, I believe that is contributing there, is that if you find the right compression driver, there are some which do not behave as if they're 1-inch diameter. They behave as if they're smaller. And then another thing you'll notice with most of the modern JBL speakers is that they've gone over to throats which are much smaller. In particular, I believe they're using 0.75 inches or 0.63 inches on a number of their compression drivers, and you'll see that in particularly their high-end home speakers. Yeah, so that's another way to get there. But again, I'm a little bit wary of that because of the number of compression drivers that you would need. So yeah, that's basically sums it up. What I'm looking to do is to create something akin to a DIY compression driver with an exit that is asymmetrical. So it could be 1 inch by 3/4 of an inch, or it could be 1 inch by 2 inch. I kind of have to figure out how far I can push things before everything falls apart. But then that would be mated to a waveguide with an asymmetrical throat. And then if this works, kind of changes the game really, unless some manufacturer starts coming out with compression drivers with an elliptical throat. Now, all right, so at this point, if anybody made it this far, there might be somebody out there who knows that this is a terrible idea for some reason, because again, I'm just I don't do this for a living. I just like to tear things down. So I may be making some really fundamental mistake. I made a fundamental mistake in the original Paraline thread, and that I didn't figure out until Todd pointed it out after 14 years. So I was under the wrong assumption for 14 years of my life. So yeah, if you think this idea is boneheaded, like they say on all the YouTube videos, say something in the comments. And are you supposed to like and subscribe? Is that what the kids say now? I don't know. Go do that.